Great. Thanks, Derek. So yeah, I'm Ian Cook, and you can find me on Twitter at Ian M. Cook. I'll post a link to the slides. They're not up yet, but I'll post a link in a Twitter in a tweet after the talk. So I was just saying to Derek before we got started that Apache Arrow is this really exciting project. And it's kind of too large to talk about in one talk. Even the R package has a number of different facets to it and can be used for a number of different purposes. So it's hard to talk about it in finite time. So I'll focus on sort of one piece of how you can use the Arrow R package in this talk. But first, a little bit of background. So Apache Arrow is this sort of cross-language toolkit for data science, analytics, et cetera. At its core, it's actually a standard. Before it was a piece of software, it was just a standard or a spec for representing columnar tabular data in memory. And then in addition to representing the data in memory, it has a spec for how to represent it on the wire and on disk. So it includes a bunch of standards. And then those standards are implemented in a number of different libraries in many different languages. So there's a big list of all the languages. Of course, R is one of them. The C++ implementation, which we'll sometimes call libarrow, it's the C++ library, is sort of the reference implementation of Arrow. And a number of these other language bindings like Python and R are just bindings to the C++ library. So that's how the R package works. It uses this RC++ interface package, CPP11, that's similar to RCPP, to interface with the Arrow C++ package. And then we can use from R all of the facilities that Arrow provides for in-memory analytics and file I/O and lots more. All of the features in Arrow emphasize performance, efficiency, standardization, and cross-language interop. I should also add that there are sort of, so Arrow is really sort of it's a package for a heterogeneous world, language heterogeneity, OS heterogeneity, and silicon heterogeneity. So it's really intended to run on, x86, 64-bit, obviously, on ARM. So, your Mac M1 chip, Arrow runs natively on that, as well as like GPUs. There's a lot of interesting projects to have Arrow run on CUDA. So there's, we're entering a world with a lot of heterogeneity like that, and Arrow is sort of ready for that. So the Arrow project started in 2016 under the ASF. It's an Apache project, and it was founded by a large group of people from many different existing open source projects. So sort of a laundry list of all of the big data and data analysis projects in the Hadoop ecosystem and the Python ecosystem at the time. One of the key founders was Wes Mckinney, who is well known as the creator of Pandas, which was a cornerstone of what made data analysis feasible for many people in Python. And although the project started in 2016, it went through kind of a long period of maturing to the point of being sort of stable. Version 1.0 was released about a year ago. So a little bit about Ursa Computing, where I work. So Wes, after co-founding this Arrow project, he founded Ursa Labs as a not-for-profit development lab to advance Apache Arrow, to kind of incubate the project and bring it up to speed. So this was done with major partnership from both our studio and 2 Sigma, and it was sponsored by a number of other organizations. So for a while, the folks working at Ursa were basically, they were our studio employees. And Wes and others received a lot of support from the R studio staff. You may have seen a few blog posts that were sort of co-written by Hadley and Wes at the time. So I know there's, a lot of Python haters and R haters, but, here you have 2 of the major characters in their respective ecosystems, and they're literally like being, paid by the same company. So, Wes has always been really serious about about cross-language interop. And that was sort of a priority from the start. Then just last year, Wes founded Ursa Computing, which what this was about is that the Ursa Labs nonprofit had kind of reached a lot of its goals. Apache Arrow, had received a great deal of uptake by many projects and a lot of users and a burgeoning developer and user community. And the next step really was to sustain that over time and continue to bring more funding and staff in. And the best way to do that is, we thought, to found a commercial company that builds enterprise products and services focused on data teams. So we raised about $5 million in seed funding led by GV, formerly Google Ventures. The Ursa Labs team continues to operate within Ursa Computing. So there's a strong commitment to continuing the not-for-profit part of that work. And we continue to accept like sponsorships from some companies just to do that work. We're also hiring. We don't have any R-focused positions right now, but there's some jobs posted there, and I'm sure we'll keep that updated with more. So a little bit about the Arrow R package. So as I said, it exposes an interface to the C++ library, and it does this in a few different ways. It has a very low level interface that enables you to like call C++ functions. So if you want to use the C++ API, call the functions that exist there by name, you can do that in R. It uses R6, which is this sort of object-oriented system in R. To expose that API. But a lot of what is most interesting about the Arrow R package is the higher level access that provides primarily through being a dplyr backend package. So when you load data in with the Arrow package, you can use dplyr verbs, to select and filter and mutate and all that good stuff, just like you could if it was a regular, R data frame. And there's also some sort of familiar generic functions in R that we implemented in Arrow as well. So the data structures that the Arrow R package uses are like data frames. The primary data structure is a table, and it's like a data frame, but it's not an R data frame. It has the same basic idea, but it's this tabular data structure defined by the C++ package and all the standards. But you can interact with it in R, much like an R data frame. And the focus of what I'll talk about today is sort of how this R package also enables a lot of data engineering and ETL type tasks in R. There's a lot more details in the Arrow R package documentation, which you can find in arrow.apache.org. And then there's a menu you can click to find the R package there. There's some great information here, but as I was saying, there's sort of a large list of things you can do with the Arrow R package, and they don't all fit into one theme necessarily, but feel free to explore this obviously afterwards. There's also some great articles drilling down into like specific topics, some of which I'll kind of cover at a high level here, but a lot more detail there. All right, and to install it, it's just installed packages Arrow. It's on CRAN. The current version on CRAN is 4.0.0.1. We had a small bug in 4.0.0, so we have a patch release up there now. But yeah, you don't have to do anything other than install it from CRAN. And if you want to install a development version, it's a bit more complicated. Normally, our folks are used to, remotes install _ GitHub. It's a little bit more complicated with Arrow because you need to install the C++ package and so forth. So check out the docs if you're interested in installing a development version. All right, so switching gears a little bit just to set the stage about data engineering. So in recent years, data engineering has really emerged, as something distinct from data science or statistics. And with practitioners who, define themselves as specifically as data engineers and very different, teams and interview structures and so forth, compared to data scientists. So there's a million ways you could define what a data engineer does or is, but I'll take a stab at it. What a lot of data engineers do typically is build, manage, and optimize systems for transforming data into forms that facilitate analysis. So that's a mouthful. But it's not about doing the analysis, about transforming data into forms that facilitate that. And what matters to a data engineer is typically quite different from what would matter to someone who's doing sort of data science or statistics. I mean, in the end, you might have some of the same goals, but sort of along the way, some of the intermediate priorities and goals are quite different. And here are just some things that a data engineer might need to do that often a data scientist, or at least a data scientist working on a team that has data engineers, would probably not really think much about. Choosing file formats for storing data and compression algorithms to apply to them based on a number of factors like the requirements of users, like what tools you're using, and so forth. How long the data needs to be around, like, is it a stable format? Does it need to do schema evolution, things like that? What's the performance need? Also things like, does it need to be human readable, like a CSV file, or is it okay for it to be a binary format? What's the cost of storing it? So how much does efficiency gain us in terms of cost? Many more factors. Typically data scientists don't want to have to think much about this stuff, but data engineers, this is like your job to think about this. Data engineers also, this is something we don't think about much in the R community especially, but data engineers need to carefully control the data types of columns in tables that they're especially writing, to avoid all sorts of problems that happen when you cast to the wrong type, or you allow an automatic cast to happen. It's very important to avoid truncation, loss of precision, floating point errors. I'll drill into what that is because a lot of folks are not familiar with that. And just inefficiencies. If you can use a 8-bit integer to store a column, then you don't want to use a 64-bit integer. So lots of factors like that data engineers think about. Before I was at Ursa Computing, I spent about 5 years at Cloudera, and was exposed to a lot of this in that traditional sort of Hadoop and big data ecosystem, where when you're storing like terabytes or exabytes of data, making a bad decision about compression algorithms or data formats or data types can be a pretty expensive mistake. Another thing data engineers care about is interop. So, if you have an ETL pipeline, what is it feeding? It might need to be feeding, multiple languages, multiple tools, Python and R, things like that, but also tools like Spark, Impala, Hive, Presto. Those are all, SQL engines. Spark, of course, can do more than just SQL, but, big data engines. And also offerings from, the big cloud providers like Athena and BigQuery. You got to make sure that the data you're writing can deal with any quirks that those systems have and interop with it seamlessly. Also things like just moving data from place to place is bread and butter in the data engineering world. So, just for instance, moving data between local file systems and cloud object storage, that's a big one. All right, so data engineering in R. This is not something you hear that much about. To date, R has, I would say, taken a backseat to many other languages for data engineering. Even Python, for a long time, as weird as it sounds, was not really the language that you'd think of when you thought of data engineering. You'd think of like Java. In the Hadoop, the sort of time when Hadoop was really a hot topic. Java-based tools were what was predominant for data engineering tasks. And Python more recently has become more of a first-class citizen in this world, but R has continued to kind of lag in this field. Of course, it's viewed as stellar for many other things like graphics and data manipulation, data analysis, but for things like ETL, R has lacked a lot of the tooling that people see as essential to perform data engineering tasks. So the R package Arrow, and Arrow, more broadly, is helping to change this. So I'll talk a little bit about how Arrow brings this big suite of tools, and a lot of the capabilities in that suite are really important for data engineering and enable you to do data engineering stuff in R that you might have in the past had to either use something like Spark for, which you can use in R, or in some cases just go outside the R language to get altogether and use like something like PySpark to do the work. So I'm going to jump out of the slides and show a few examples of the data engineering tasks that I was referring to. All right, so one of the most common things, again, that a data engineer cares about is being able to read and write data in popular file formats and using common compression and decompression algorithms. So a lot of what data engineering is about is accommodating the needs of these systems, like I was describing, these big data warehouse systems and Hadoop SQL engines and things like this. So if you look, for instance, at what file formats Spark can support, if you have a Databricks-based system for your data team, then you need to make sure that the version of Spark that's running on your Databricks platform can support the file formats, the compression algorithms that that you're writing your data in. And a very popular format for in the data analysis field for storing data is Parquet. It has a bunch of benefits, but it's a binary columnar format. It's highly compressed, and it also has really good read performance and a variety of access patterns. And it's become really probably the #1 format in sort of the data warehouse space. So one of the key features of this Arrow package is that it can read and write Parquet files, and it can do so using using the Arrow library, which has a reference implementation of Parquet built right into it. So this is sort of like first class Parquet read and write support, and we expose that through the R bindings. So here's an example. And this is fairly basic, but I'll point you to some additional examples later on. So I'm going to load a few packages, Arrow, dplyr, and for some example data, the NYC Flights 13 data set. And then I'll just create a simple result set based on that flights data set. This could just be anything, but I've just got the flights that departed. So this NYC Flights 13 data is flights that departed out of the New York City airports in 2013. So I filtered it down to the ones that departed, that had the destination of Indianapolis. And so I've got this result data frame, which is just 2,000 rows. This is not big, it could be much bigger, but now I'd like to write it to a Parquet file. So one of the really neat things about the Arrow R package is that this function write Parquet has a lot of different options, many of which you probably wouldn't understand unless you spent a long time sort of working in the data engineering field. Like most of us are never going to touch use deprecated int 96 timestamps, but there's someone for whom that is really important. And so there's a whole bunch of features like that here. I'll highlight the compression features and a few other features to see sort of like what the differences are in the resulting file based on whether you toggle them on or off. So the default compression format for this write Parquet function is this compression algorithm called Snappy, which is really widely used. So there I wrote a file using that Snappy algorithm. Next, I'll write the same data to a file that's uncompressed. And then next I'll write one using Z standard compression, which is this really high performance compression algorithm. I think it came out of Google. So let's look at the resulting files. So the uncompressed one is 13 kilobytes, Snappy is 11 kilobytes, Z standard is 9. So this is 2,000 rows of data. You extrapolate to billions and billions of rows, and you can see how these decisions, or the ability to exercise these compression algorithms so easily, is important if you're a data engineer. If you're putting this data into Amazon S3, and then your data analysts are going to be querying it out all that egress cost will be much lower if you choose the right format. And then there's some other options you can use too. For instance, one of these columns in the data is two of the columns are factors. So I factored the carrier and origin columns. And I can decide whether or not I want that to be encoded in a dictionary. By default, it is. Just like R used to have default character encoding was factors. Now it's not. But Parquet can store data much more efficiently by indexing the distinct values in a string array and then referencing them by like small integers. So if I turn dictionary compression off, the file really blows up to 86 kilobytes because now instead of like JFK, EWR, and LGA, the 3 New York City airports, each being represented once as a character string and then thereafter as integers, now these are represented as the characters in every column, so it takes up a lot more space. And then there's some other things like chunk size. These are the sort of things that you might want to control based on access patterns of your data. So for instance, in data engineering, if you are primarily writing data that is going to be read in batch sort of jobs, then you typically would want like larger file sizes. You don't care about things like chunking so much, just put everything in the biggest chunks you can. But if you're going to be having data that's accessed in like more of a random, access pattern, you might want to use smaller files, smaller chunk sizes, things like that. So let's see what happens to that. Where is it? Tiny chunks. Well, that really blew up the file. So if you chunk up the data into really small chunks, then the compression algorithm can't do things like dictionary encoding or it doesn't have the data has more entropy, so it's like harder to encode efficiently. All right, so that's an example just of how you can use the write Parquet function. There's also a read Parquet function, which has, it's actually the same help file. This has some other options available to it. And there are a variety of other file formats that are supported by the Arrow package, and they're all described here. Zoom. In addition to Parquet, which I said is a really popular format in the broader world of sort of data warehouse, data engineering work, there's also a file format called Feather. It's also called the Arrow Interprocess Communication, or IPC format. This is a format, Feather is a format that was defined by the Arrow project. And essentially what it is a representation of the memory when you load data into Arrow on disk, so that when you read in a Feather file into Arrow, you don't have to do any serialization or deserialization. It just picks the entire thing up more or less and dumps it into memory as like one unit, like byte by byte, off disk into memory, and that it makes for really efficient reads and writes. Although the files are a little bit bigger than Parquet files because, of course, they that's not going to compress as well. So that's another file format. That's less about interop, but more about sort of efficient temporary storage. That same format is used to send data over the wire as part of the wire formats that Arrow defines. And then, of course, there's CSV and JSON and tab separated as well. That's all supported by Arrow. We have some additional work coming. I think in the 5.0 version, we might have support for writing ORC files, which is another, and reading ORC files is another popular format in the sort of Hadoop ecosystem. All right, so that was the first example. So second example, I'll move on to this other thing I mentioned that data engineers really care about, which is floating point errors. And this is something that is not really well understood by statisticians. It's probably better understood by software developers than by statisticians or data scientists. So in order to demonstrate this, I'm going to use Arrow, dplyr, and sparklyr, which is this R interface to Spark. So I'm going to load those 3 packages. And then I'm going to start a Spark connection. Oh, I guess it's already open. So one of the interesting things, if you've ever used Spark, either with SparklyR or SparkR, is that you need to create, or with any other language for that matter, you need to create like a Spark session to run your work in. And this exists in a sort of JVM that sits alongside whatever session you're doing the work in. Arrow is not like that. So the Arrow library is baked right in to the process that you're using in R. So there's no like need to start a separate engine or install a separate engine, which you need to do with Spark. But I'll use Spark here just to demonstrate a third-party tool that does SQL queries and data analysis, and that also can consume Parquet files. So hold that thought. This is something that a lot of people don't know about floating point numbers. So if I take 0.1, 0.1, 0.1, add those together, and then subtract 0.3, the answer is not 0. The answer is a very small number, but it's not 0. This is because of floating point errors. It's impossible to perfectly accurately represent a floating point number in computer memory, and these sort of errors, they often don't matter for data analysis, but for other sort of transactional systems, these sort of errors really matter. And although this may seem like a fleetingly small error that would take you could just round it, right? That's true, except that in some contexts, these floating point errors can accumulate and actually become significant. And that is the bane of the existence of every person who runs a transactional database system that needs to be accurate. For example, if you add money to your bank and take it out, the same amount of money out, you want the balance to be unchanged. And R has no way. So, well, let me before I get onto that, I'll just show that the same error happens if I create a data frame with those values in a column, like you would see in a transaction log, and then use like dplyr summarize to compute the sum of those numbers. It's a slightly different result here, but you can see there's still a small floating point error. Another thing I'll demonstrate is this is not unique to R. If I write that same data to a Parquet file, and then I use Spark, this is the SparklyR Spark read Parquet function, to read that data into a Spark data frame. Now we have the same data, but this is a Spark data frame. And then I use dplyr on the Spark data frame or SQL on the Spark data frame. You get the same thing. And if you use almost any query engine, you get the same result on floating point data. You get these weird small errors. So the solution, there's multiple solutions, but the solution that's most widely used for avoiding these floating point errors is to use fixed precision decimal numbers. And this is a sort of data type that you can apply to data. It's not supported in R natively, but Arrow adds support for a way to represent fixed precision decimal numbers in R, as well as in all of its other language bindings. So we're going to start by creating, let me clear this, not a R data frame, but an Arrow table. So what this is it's this table of the same size, but it's represented in the C++ library. If you want, you can use dplyr to collect it, and it becomes a data frame, or you can do as data frame, and it becomes a data frame. But until I do that, it doesn't actually exist as an R data frame. This is the Arrow object that is equivalent to an R data frame. And for more on that, just to quickly interrupt myself here, there's where is it? There's a nice, okay, it's here. There's a nice article that describes how, I think it's in Getting Started actually. Yeah, there's a nice object here that describes the various data objects that exist in the Arrow package, and sort of what they are, what is their dimension, and what are they most similar to. So there's a scalar class. R does not have a scalar class. Everything is a vector in R. But Arrow defines a scalar class. There's also arrays. There's chunked arrays, which is sort of a generalization of array that is suitable for breaking into pieces. Record batches and tables. Table is the one you interact with the most in Arrow. A record batch is very similar, but the difference is that tables can be chunked up, record batches can't. And then there's this thing called a data set, which I'll talk more about in the next example. But so Arrow defines all these parallel structures that are different from what you have in R. And you want to familiarize yourself with that if you start to use this package. So I created this table, this Arrow table. And now what I can do, and I created it just by passing this vector, same vector of values. But now what I can do is say, let's cast that column, that amount column, to decimal, which is one of the Arrow data types. And if you want to see all these Arrow data types, there's a Arrow data types help file here. And you can see this really gives like the full complement of different data types that you'd find in a data warehouse system or in Parquet files or things like that, and various arguments that you need to parameterize the ones that have parameters. So I have cast, just make sure I rerun this, I've cast that, that amount column to a fixed precision decimal number. So now it doesn't show up as a floating point, it shows up as a decimal number. Now I'm going to write a Parquet file using the same write Parquet command, but I'll write it to a different file. And now if I open that up in Spark, it looks the same here, but when I compute the sum, it's actually 0 because fixed precision numbers don't have those floating point errors. Same here. So this is the kind of stuff that it's vital to get right as a data engineer. Even sparklyr unfortunately does not have a way to carefully control the data types of columns as you're writing them to different file formats. So Arrow has that, and it's one of the features that's sort of most important if you're doing this kind of work. Great, and the third example I'll talk about is about working across file systems and also just working with very large data sets that might be in a remote file system. So Arrow provides a set of functions that I demonstrated before. Oh wait, I wrote the wrong thing here. Hold on. Okay, so Arrow provides a set of functions that you can use to interact with these, file formats, read and write Parquet, read and write Feather, and also the read and write CSV, JSON, TSV functions. And all those functions can accept as their first argument either a local path to a file in your local file system or a S3 URI, which points to a file in Amazon S3. I think, eventually we hope to add support for other major cloud object stores. Right now, it's just Amazon S3. So I can read data from a local file, and this is a fairly large file. It's like 300 megabytes. Or I can read it from S3. Of course, it's going to take a lot longer to read from S3. It's got to pull it down, but you'll get the same result either way. So there's no special functions you have to call in order to work with the data in Amazon S3. It's just the same function with the protocol at the beginning to let Arrow know that's that's in S3. So that's still running. So I'll talk through this next one. There's also this set of facilities that Arrow provides for working. That was Spark dying in the background there. There's also this set of functions that Arrow provides for working with large multi-file data sets. And this is exposed through this open dataset function in the R package. So you can also use this on data that's in your local file system or in Amazon S3. So here I'll open a local data set, and notice that happened instantly. And here I'll also open a a data set in S3, and that happened also very fast, because what happens when you open one of these data sets is that it doesn't actually read the data. It just examines the file system, lists all the files that are in this folder that you, or bucket in the S3 case, that you provided, and then picks up their metadata, and then it has information about how it could construct a query on those files. So here I've passed another argument, partitioning year and month. And what this is I'm telling Arrow that there's a directory structure underneath this top level S3 bucket that is first indicating what year that the data is and what month the data is. So this data it's over 100 Parquet files, but it's arranged in this directory structure. It represents the New York City taxi data set. It's arranged first by year into folders and then by month in subfolders. So passing that partitioning information can allow Arrow to even more efficiently construct a query on that data. It would still take a while to read all that data from S3. So I'm gonna construct a query on the local version of it. But here's a complicated dplyr query against 125 files, all of which are quite big. I mean, I think the total size of this is like many gigabytes. And I think it's like on the order of 30 gigabytes. But because I filtered by one of the partition columns, it was able to ignore like almost all that data and just look, not even read it. Just like look at that one partition and only read the files there, and then efficiently filter and mutate and so forth the data there. So if you're interested in that capability, there's more information in another vignette that's called Working with Arrow Datasets and dplyr. It's a vignette in the packet, in the Arrow R package, and it's an article here on the R Arrow docs website. So lots of other information about what's possible here. You can also write data sets, which gives you an ability to write out multi-file data sets partitioned by column of your choice. So this enables you to take a much larger than memory set of data and work with it, using the the limited memory you have on your laptop, say, and then write files out, large collections of files out, all without that data all residing in memory at once. So that is all the capabilities I'll describe today of the Arrow package. There's many more here. So yeah, feel free to peruse this website. But I think we have time now for questions.
Awesome. Thanks for the great run through of the Arrow package and its capabilities. I want to open the floor up to anybody who might have questions. Go ahead and unmute yourself if you do have a question. And if not, then I have a lot of questions. So, all right.
I think I have one.
Oh, go ahead.
Yeah. Sorry. So I'm new to the Arrow package. I've never used it before. But I work in the healthcare industry, and majority of the time my job involves accessing remote data from databases. And sometimes some of the queries are so complex, and it's a little bit difficult to collect the data from those remote tables. I was wondering if at all I can use this package to simplify some of those processes.
Yeah, so what sort of is the data in a typical sort of SQL relational database?
Yeah, so it's usually on Oracle database. Right now we are migrating to Snowflake, but majority of the time I'm working with, I don't know, 9-10 million rows of data. And collecting that data set has always been an issue because of how big they are. So I don't know, I'm just curious if at all I can use this package to somehow simplify some of those processes.
Yeah, that's interesting. I think right now there's not a lot of features in the Arrow library or the broader project that deal specifically with that problem. I mean, I'm sure in R, there's like lots of other tools like dbplyr,
Yeah.
which are great for working with relational databases, and dbplyr. Yeah, I mean, dbplyr is the tool I would turn to for that. Of course, one of the things that Arrow might help you with is that if you want to, construct a system whereby you like pull data, you extract data from that database into like a downstream system to avoid having to like live query the database. So if you have some caching layer or something like that, it absolutely might be, wise to use like the Parquet format or the Feather format as like that, that data, the data storage format for that like caching layer. But yeah, there's no sort of direct connection to RDBMS systems that Arrow provides today. I think our long-term vision at Ursa Computing is to help with those sort of problems. Like one of the systems that's part of Arrow is called Arrow Flight, and it's an interprocess communication wire format, layer that you can use to very efficiently send data down the pipe. And it just does so like in the most efficient format, and it uses parallelism and so forth to really get blazing fast speeds. So long term, I think we're interested in doing things like if you have your data sitting in Snowflake or in some third-party system, you could create an endpoint that's close to that system. It's like running in the same cloud provider, the same subnet or whatever, and then call that endpoint to get absolutely the fastest possible stream of data out of that system and into your client, because the formats like ODBC and JDBC that we often use to extract data from databases, they're convenient, but they're like quite inefficient in many cases in terms of like how long it takes for that data to come out and how well they use like processors and memory to speed themselves up. So yeah, stay tuned. I think we're going to do a lot more in that area, and it'll be fascinating to see what we do there.
Interesting. Thank you so much.
I think that brings up a good point about like, in what cases would you, like what types of projects do you see people storing data in a database versus storing it in like something like a Parquet file or a Feather file?
Yeah, I think I don't think we would encourage the use of Feather for like really long-term data storage, but Parquet absolutely, that has for a long time been sort of the gold standard of long-term data storage in big cloud data warehouse systems and Hadoop clusters and so forth, and Amazon S3 and such. I think that the original idea of a relational database system, or like Oracle or Teradata or Netezza or Vertica or any of those like traditional big data warehouse or RDBMS systems, the idea is that they fully encapsulate access to the data. You don't know what format that data is in, and they don't want you to know or care what format that data is in at the byte level. That's below the level of abstraction that they want you to care about. You tell the database, I want the data, by giving it a query, and it gives you the results, but you can't like get around the database to access the data. The advent of Hadoop and all of those sort of modern analytic database systems that came at the same time as Hadoop changed that game a lot. For instance, any of those engines that I enumerated earlier, like Spark, Hive, Impala, Presto, Drill, Amazon, Athena, BigQuery. The primary way that those work is you just have a directory of files. Like often they're Parquet files. They could be CSV files. It's just a directory of files in some file system. It could be in S3, could be in Hadoop distributed file system, HDFS, could be just on local disk, and you just point the query engine to that set of files, and it queries them directly, and it can do so with tremendous efficiency. I mean, that was query engines like Impala and Spark that was the main contribution that they made, is matching the performance of highly tuned relational database systems in many cases, even though they didn't fully control the data format. Those systems are not great for like transactional databases because they're primarily intended for sort of reading and analytic workloads. But yeah, that's like that is so when Hadoop became really popular, sort of in the late first decade of the 2000s, that was the real innovation. It's like, hey, you don't need to have only one application control access to your data. You can have your data sitting in a directory, and you can have Spark access it, and you can have Impala access it, and you can have Arrow access it. And they're not, you don't need to go through one choke point. All of those engines can access the same data as long as it's in a standard format. So I think, yeah, I mean, if you want to not be sort of stuck with a vendor who maybe isn't treating you real well, or dead-ended into some sort of like sharding issue that your database may have under a very high concurrency and a large volume of data, I think adopting that modern modality of having data in files in a format like Parquet in a directory just opens up the ability to use so many more tools. And although like Hadoop per se is not like such an exciting word today, like no one thinks, oh, Hadoop is like the exciting new thing anymore. That is a long-term effect that it brought to the world that is absolutely not going away. It's like the legacy of that Hadoop era is that data is now often stored in formats that aren't fully mediated by a relational database system. Sorry, that was a really long answer.
No, I think it's really informative because, like, as you were going through some of the examples and uses for the different file types, I was thinking to myself, I wrote down a question. I was like, one of my little side projects is like to eventually put up a bunch of sensors around the house or whatever and collect maybe some like temperature, humidity or something like that and store it somewhere. And I think, okay, well, I could put it in a database. Like, where do I host the database? I'm much more comfortable just saying, okay, each sensor, how about you just write your data to a file in a directory, and maybe I throw that up on S3, and then whenever I have an application, each of those applications can just talk to the S3 bucket or something like that, And
Yeah.
it sounds like maybe like if I was to run this little experiment over a long enough period of time, like a Parquet file might be the type of file that I want, because it like I could be generating tons of data. But I mean, I don't know. Maybe there's some cost to like writing the Parquet file, like if I have my sensor like writing every second, like temperature and all this stuff. Like,
yeah, there's this, that's interesting, like, because there is this problem with that that modality where you just write data to files and then have the query engine just access the files. One common problem is called the small files problem, where when your data is in many, many small files that just have a few records, even, hundreds or thousands of records instead of like tens of thousands or millions of records per file, the efficiency of those big data query engines goes down, down, down. So the efficiency of an engine like Spark comes from the ability to just like rip through a file, and rapidly consume like many, many rows of data. And also the efficiency of these formats like Parquet come from the fact at a file level to compress data by looking at like repeating patterns in the data and so forth. So, I mean, for your project that you're doing with your temperature sensors, it might not matter. But, S3 buckets stop performing as well when it becomes very time consuming to just list all the files in the directory. Because then suddenly the S3, API, it has to look through all those single line text files of your temperature records, and the efficiency drops. So, maybe in that case, it'd be better to use like SQLite or DuckDB or something like that. But yeah, these are, again, it's like I set you up to, discuss the questions that data engineers spend all day thinking about. So yeah, it's not trivial thinking about those things.
One of the things that you brought up was the ability to take that table data type that's a part of Arrow and convert it over to, or maybe represent it as a data frame. And
Yeah.
I was wondering if you have a table in an Arrow and you have set a field to be like a fixed floating point value or a fixed value field. What happens to that setting once it gets converted over to a data frame? Does that field or that data type stay with it?
No, so R doesn't have any native way to represent those data types. So if you create an arrow table and you carefully construct the schema to be, certain data types, and then you convert it to an R data frame, all that's lost. I mean, it does its best job of mapping the types, right? So, a fixed precision decimal number becomes just a numeric, a double numeric in R. You can store the schema separately though. So if you want to like not store the data, if you want to take the data and represent it as an R data frame, but then like preserve just the schema is an object type in Arrow. So you can hold that. And then when you create it again, you could just apply the same schema. But yeah, there's no way, unfortunately, in R to preserve additional data type information in a data frame beyond that which R provides. There are a few, like one interesting thing is that R does not have native support for 64-bit integers. And a lot of database systems and Arrow also use large 64-bit integers. If you try to create those you try to sort of naively convert those to R data frames, they'll convert to numeric, not integer, because numeric can store larger integers than integer. So then there's this R package called bit64, which can represent 64-bit integers. So there are some weird cases like that where some third-party package comes along in R and can represent that data in a data frame. The bit64 package does that. Someone could come along and create a package for R that allows fixed precision decimal numbers to be represented in a data frame. And I would be really happy if somebody did that. That'd be awesome. But right now, it just gets converted to numeric, and all that, fixed precision stuff is lost. Yeah.
With the table, can you, I think you mentioned something about this, but you can do your dplyr operations on the table and it stays as a table?
Yeah, exactly. Let me jump back to
Okay.
Demo for that. So
in that case, there may not be a need to turn it into a data frame. You just treat it as if it was a data frame like object, and it will respond to all your R commands.
yeah, exactly. So here I ran this command, read parquet. And if you look at the documentation for read parquet, its default behavior is to return an R data frame. So if I look at this taxi.local, it's an R data frame. I can do, you can view it in the RStudio viewer, although, it's probably going to like freeze up my whole computer because it's 13 million rows. Close that quick. But if I instead run this with as data frame equals false, it'll finish a little bit faster because it's easier to construct an arrow table than it is to construct an R data frame, because we're just working with purely in the C++ layer at that point. And then what I have is an arrow table, not an R data frame. So if you look at class, you don't get data frame, you get this sort of hierarchy of arrow data structures. Table is the primary class. It also inherits this class arrow tabular and some other classes, just to say that it's like an arrow object. And it's, like I said, it uses the R6 type system. And yeah, you can just do, filter, I forget what, year equals 2015, or no, there's only, we do month. Well, no, I'm forgetting what, okay, I can do total amount greater than 100. and that'll directly filter that data to the the rows that have where the fee amount was like larger than $100 US. And then I can do a couple other things. I could collect the result after applying the deployer operations to it, and that'll give me a data frame, smaller data frame. Or you can also keep it in the Arrow world by calling collect. If you collect has, hold on. Collect has an option as data frame equals false, and then it stays as an R object, but it materializes it. Sorry, it stays as an Arrow object, but it materializes it. So it uses lazy evaluation, basically. Until I call collect, or you can also call compute is a synonym for collect as data frame equals false. Until you call one of those functions, it hasn't actually performed any computation. It's just stored a record of what dplyr verbs you have told it to perform. And then it only actually performs the calculation when it's needed. And then depending on if you call it collect with as data frame false equals true, or if you call it compute, then it either returns an R data frame or it returns a materialized Arrow table. So yeah. So we have limited dplyr support right now. You'll notice that most dplyr verbs work. Group by does not work. Well, in most cases, it doesn't work. And aggregate in most cases doesn't work. That is going to be coming in the next, I hope, in the next release of the Arrow R package. Right now, we support most of the other dplyr verbs. Filter, mutate, transmute, select, rename, and some of the other like lesser ones. But support for group by and aggregation together is going, we hope, to come in the 5.0.0 version of the Arrow R package.
There was a question in the chat. I think you kind of addressed this maybe a little bit earlier, but it says, any plans to work with other cloud object storage, Google GCS, or Azure Blob Share?
Yeah, I think we're going to get ADLS Gen 2, the Microsoft Azure, blob storage system fairly soon. That's pretty highly used. And I think it's a priority eventually. I don't know exactly when, but it's a priority sooner rather than later to implement, support for ADLS Gen 2. I'm not sure about Google Cloud. And I should say that the S3 connector also supports like other S3 mimicking file systems like MinIO or others like that. But yeah, well, absolutely, it's on the roadmap. I'm not sure when exactly it'll come, but it is a priority, especially for Azure. Oh, and I should say also, I think HDFS is another one, for the Hadoop clusters. The Hadoop distributed file system is another file system. And I think there's already support for it in the C++ Arrow library, but I don't think we've implemented support in it for R yet. But
yeah, I was looking at the docs and I saw it for the C++, but I didn't see it for the R yet.
Yeah. Hey, if you want to open a pull request.
All right.
Yeah, and I should say, if anyone is interested in contributing, we've got some information on the website about how to get involved. The project is a bit difficult to contribute to because we keep our issue tracking system in Jira, not GitHub issues. This is the way a lot of Apache Software Foundation projects are run. So it's a bit of a hill to get over to first contribute, but we're friendly and we love first-time contributors, even if it's just fixing typos in the docs. We love it for folks to get involved. So yeah, please check out arrow.apache.org if you're interested. One thing I mentioned I was going to say at the end also is that if you're interested in finding out more about the Arrow R package, there will be a talk given by Neil Richardson, who is my manager at Ursa Computing, at the UseR 2021 conference, which will be all virtual this year. So look out for that. I'm sure that'll be an interesting talk. I think Neil will highlight some of what's new in the R package, and we might have the new version of the package up by that time. So yeah, stay tuned.
Any last questions? Well, Ian, I'd like to thank you for explaining and sharing with us the Apache R project, or the Apache Arrow project, and a little bit about what's happening over at Ursa Computing. Thank you for joining us today.
My pleasure. Thanks for the invite, Derek.
All right. I'll talk to everyone soon.
Thank you.